Cool, so we'll get started in just a couple of seconds, but if you're one of the 8 or 9 people who have not voted in the poll, please vote on that just to see how everyone's feeling about iterators and generators. And yeah, just some introductions throughout this session. As you could probably see, you can message people in the chat. So feel free to ask any questions in the chat, or if you want us to clarify anything or go over something again, either Connie and I will be keeping an eye on the chat at all times. So yeah, please ask questions there, and we can probably get started. So yeah, welcome to the Iterators and Generators review session. We can do introductions maybe. My name is Catherine, one of the TAs for this class.
I'm Connie and I'm a tutor.
Cool. And yeah, we're here to talk about iterators and generators. So as a rough timeline, we'll just be doing kind of an overview of some conceptual concepts in iterators and generators. And then at the end, we have 5 problems, a mix of just random problems and past exam problems. So yeah, keep going. And throughout the session, maybe we'll have technical difficulties since we're going to switch screen sharing. So just bear with us if that happens. Cool. So yeah, starting out, let's start by talking about iterables. So as you know, in iterators and generators, we have 3 main concepts. We've got iterables, iterators, and generators. So starting off with iterables, an iterable is any object that has some elements that can be looped over. So for me, my general rule of thumb is if you can do a for loop over something, it's an iterable. So some examples that you've seen even before iterators and generators are strings. For example, you can do a for loop over a string. It will give you each character at a time. Lists are probably the most common thing. If you for loop over a list, you'll loop over every single element in that list. And also dictionaries. If you loop over a dictionary, maybe you haven't seen this before, but you'll go through every key in that dictionary. And iterables are nice because there's a lot of different functions that can aggregate iterable arguments together. These are useful for iterators and generators, and they're also really useful for tree recursion. So some functions that you might have seen are sum, max, and min, which are very useful for, especially for iterables of integers or numbers. Also all and any, which are really useful for Boolean operations, for aggregating Booleans together. You might have also seen several of these built-in functions that may take in iterables. You might have even implemented some of these in the scheme project. Map, filter, zip, reverse, list, tuple, sorted. Don't worry if you haven't seen this. Remember that in the exam, you always have access to code.cs61a.org, so you should be able to access these at any time. And now bridging the gap to iterators, there's a special function iter that you can call on any iterable, for example, iter of 1, 2, 3, which is going to give us back an iterator. So next slide. An iterator is an object that keeps track of a location inside of an iterable. And we'll see a visualization of what this looks like a little bit later on, but you might have heard this analogy in the past. You can kind of think of it like a bookmark. If an iterable is a book, for example, you can for loop over a book or flip through the pages. An iterator is kind of like a bookmark where you have a specific location at some point in time. And this analogy also extends because you can have a lot of bookmarks in the same book, and similarly, you can call iter on an iterable several times, so you can also have several iterators all dealing with the same iterable. Again, later on, Connie will show a good visualization of an example of this. The special methods we have for iterators are mainly the next method, where you can call next on any iterator that gets the current element and moves the bookmark to the next element. So this is mainly how you go through an iterator. And another method is, since iterators are iterables, you can call the iter method on an iterator, and that's just going to go ahead and return itself since it's already an iterator. Next slide. And for iterators, to know when you're done looping through this iterator, if you call next on iterator that has no more elements, it will raise this stop iteration exception. Maybe you've seen this before in your code. And this is an exception or pretty much an error. So if you don't catch this, which there's more about it in the exceptions lecture, I think, this is considered a Python error and will just stop your program completely. So you have to use this try except block to catch these errors. And this is actually why people like for loops so much, because that's kind of built in to different for loops. And I think we'll see what this code looks like maybe on the next slide. So next slide. Cool. Yep, we'll see it here. So you probably used for loops at some point throughout CS61A. So here's an example. If you have a list, again, you can for loop over any iterable, including lists. So let's say you have a list counts as 1, 2, 3. You do something like for item and counts print item. That's going to loop through print 1, print 2, and print 3. this is exactly equivalent to this code on the right, which is just actually the magic behind the for loop. I think this was in the textbook. Don't remember if it was in the lecture, but I think it's pretty cool. For looping over an iterable is the exact same thing as, let's see if I can annotate. First of all, creating an iterator out of that iterable, which is just calling this iter function over here. So you create this items iterator, which is an iterator over this counts iterable object. And then we need this try except block. And we need that because we're saying, well, basically keep calling next on our iterator until we have no more items. So that's try getting the next item and print the item. And if we run into the end of this iterator, we'll get the stop iteration and we'll pass, which means we're just done with our code block over here. So these two are exactly equivalent. For some item in iterable print item is the same as try while true. Keep calling next on the iterator of this iterable until you get a stop iteration and then stop. Cool. I'll pause here. Actually, I think I have one more slide. So next slide. Cool. And just a summary of these three things we've talked about, even though we haven't talked about generators yet. We'll talk about that in a bit. We have this wide group of Python objects that are iterables. Anything you can call a for loop over, basically anything that has some sort of ordering to it. You can call iter on any iterable to get the iterator, which is more specific because you call next on it. It has a specific location at a point in time. You can like march the bookmark forward. So the main method here is next. And then later we'll talk about generators, which are specific iterators that I kind of just think of them as iterators over different functions. So I think this diagram is really important because this shows us what tools we can use. We can call next on a generator, but we cannot call next on a list. We can for loop over generators. We can yield from generators, etc. So this is just very important to keep in mind. Cool. I'll just pause here really briefly to see if there's any questions. I see two in the chat. First one, does calling iter on an iterator create a new iterator or the same one? So I think in the slides earlier, it said that calling iter on an iterator is just going to keep the same one. So this is kind of tricky because if you do something like get to the end of an iterator and then you call iter on that same iterator, it's just going to be in the same location. It's going to be the same exact iterator. So it will keep the same one. Next question, does the end of each run through the while loop return to the try statement? Let's see. Oh, yes. So oh, wait, this might be bad. I might need to swap the ordering. I copy pasted this from the textbook, so I'll blame the textbook if this is wrong. Try while true. Oh, so basically what's happening here is we have this giant try block, which says just execute this code. At some point, there's probably going to be an error. So it doesn't matter when. Let's say we get a stop iteration 3 items in. So while true, get next item, you print the 1, next item, print the 2, next item, print the 3. You loop back into the while, you'll get a stop iteration, but this whole thing is within the try block, so we'll accept the stop iteration and just pass or stop the program there. I think this is probably fine too if you swap the while and the try and move the except inside. But yeah, for more points on that, you can watch the exceptions lecture. Cool. There's time for like one more question if anyone has any questions. All right. Cool. If not, then we can move on to the next example. Again, please feel free to ask questions in the chat. I'll like type responses. Oh, wait, there's another slide. I'm sorry. So extra methods that you can use. There's this list method, which you can call on any iterable. You've probably seen this calling list on other lists to create a copy of it. So under the hood, what's going on is we're going to get an iterator out of that iterable, similar to the for loop. And then it's, again, similar to the for loop. It's going to keep calling next until we get a stop iteration and put all of those items that you got from calling next on it into a new list. And so one tricky thing is calling list on an iterator will do the same thing, which means it will march you all the way to the end of your iterator. So this is kind of like a warning. If you call list on an iterator, the next time you call next, you're going to get a stop iteration. So even if you call list on an iterator and then call iter on that iterator, it will not refresh the iterator since it returns the same thing.
Yeah, now we have a small example. But yeah, if you have questions, you can drop them in the chat and we can also answer them as we go along. But here we just start out with a list being 1, 2, 3, 4, 5, 6, 7, and we see it displayed on the right. And we create an iterator I1, and we also create, and there's I1 like pointing the bookmark. It's just pointing to the beginning of the list since we haven't called next on it before. And we have I2 as another iterator pointing to the list. So it is its own separate bookmark, pointing to the beginning of the list again, since we haven't called next again. And we have also I3, which is an iter on I2. So what that means is just returning the iterator of I2. So we're not going to have another separate bookmark for I3 since I3 is iter of I2. So it is the iterator I2 itself, not a new one. Then next we have, we called next on I1. So we can move the bookmark forward for I1 only to 2, and then we return 1 since before I1 was pointing to 1. And I2 still hasn't moved because they are separate iterators. Now we change list of 0 to be 33. So instead of 1 as the first element, now we have 33 here. And we see that now if we call next on I2, since I2 is still pointing to the beginning of the list, 33, it will yield 30 or like return 33, and it will advance its bookmark. And it doesn't remember that the list used to be 1. It was just pointing to whatever that list has, and it returns whatever the list has currently in the position. Now we have next of I1 again, so we advance I1 to 3, and we return 2. And we have next of I1 again, and we advance it to 4 and return 3. And now we have next of I2, so we can advance I2 from 2 to 3, and it is independent of I1. And now we have next of I3. And so remember that I3 was iter of I2, so it is the same iterator as I2, so it will move the same bookmark as I2. So it will actually move I2 from 3 to 4. So now I1 and I2 point to the same location. And now we have another example of what would Python display. So we have a different list of 1, 5, 4, and 3. And we have I equals iter of the list, and we have next of I. So next of I would just, since I is still pointing to the beginning of the list, and the beginning of the list has 1 as the 0th element, so we can return 1. Oh, sorry, and then I can explain the next part. I didn't know it would appear, but we have j equals iter of list, and j is a separate iterator. Since we called iter of list again, we didn't call iter of I. So if we call next on j, it's its own bookmark, so it will still return 1. It is not like connected to the bookmark of I, which if we called next on I again, it would return 5. And I think we have another example of a different Python displaying question. So we have a list of 1, 2, 3, 4, 5, and then we have I equals iter of list. So when we call next of I, we get 1 since it was pointing to 1 and now it points to 2. And then we call next on I again, and it points to 2, so we have 2. And then now I will point to 3. And then we say for underscore in range of len of list, print next of I. So underscore, we usually just put that if we're not printing or we're not using like the variable in the for loop, like actually in the loop, but it's just a notation thing, so it doesn't matter. You could have put like for j in range or anything. And so we know that the length of the list is 5. So when we go through this for loop 5 times, we have print next of I, but remember we've already called next of I twice, so I is pointing to 3, so we can print 3, print 4, and print 5, and then the for loop is still going since it was going to go for 5 iterations. So when we try to do that, it will give us a stop iteration. So we see that here. And let me check the chat for questions. We see that.
Oh, yeah, you can answer
Sorry.
that question. I'm struggling to type stuff.
Sorry. Calling iter on an iterator does not refresh the bookmark, so it will start where it left off. It will also permanently move the bookmark to the end. What does this mean? I think they were saying, so calling iter on an iterator does not refresh the bookmark, so it will start where it left off. So kind of like when we did the example, wait, sorry, let me go back. Okay. When we had when we had I3 equals iter of I2, it's like the same iterator as I2. So it doesn't, like I3 isn't a new iterator, so it doesn't point back to the beginning of the list. Like if I2 was pointing to like 3 and then we called iter of I2, I3 would still be equal to I2. So if you called next on I3, it would be the same as calling next on I2. So it would just print 4 if it was pointing to 3 before. I think the thing about the book, like the not refreshing thing or permanently moving the bookmark to the end, I think that might have been an error in our slides. I think that might have been referring to like lists, but correct me if I'm wrong. I'm not sure. But I think when they said like when we call lists on something, like we iterate through everything on the list and then we just have the bookmark pointing to the end. Okay, and let's see. We said we have that if you have next of A, oh, sorry. If for the example in the chat, which is, yeah, I guess I can annotate. In the chat, we have A equals iter of 1, 2, and 3. And then we have B equals iter of A. And then B is A, which is true, since they're the same thing. And then we have, if we called next of A, is B of A still true? Yes, it is still true because it's pointing to the same object. So if you called next on A or next on B, they would both be advancing like that same bookmark. And then, okay, sounds good. And then, yeah, if anyone else has other questions, please drop it in the chat. Let's see.
Sorry, real quick. I saw one question. When would we ever want to call iter on an iterator? I actually don't really know. I tried to Google this, so if anyone has any answers, feel free to type it in the chat.
That's true. Maybe like saving it, like making a copy. Like sometimes we want to copy lists, but I don't really know why you would want to have something else pointing to the iterator because unless you like changed it. I'm not sure.
Great
For
answers.
De Niro, yes. Let's see. For the first, what would Python do was one printed even without the print statement. So I think that we were just, oh, sorry. Like next of I returns 1, and then, so that's why we just have 1 like displayed. Like in the interpreter will like try to display what is 1. If it was a string, like if next of I was like, it was like, let's say we had oh, I'm not annotating, sorry. Oh no, wait 1 second, sorry. I might have had the zoom bar, but that's okay. If list was a string and we had like De Niro or something, if we called next of I, the interpreter would just display like D with like quotes around it, but if we printed next of I, then it would have like D without the quotes around it. But it will still like return that. And then, sorry, I think I have disappeared the chat from my computer, but if anyone else had other questions, would y'all be able to let me know?
I think I'll. Oh, one more question.
Oh, sorry. I think I can't not read the chat.
Oh, no worries.
Unfortunately,
Here,
sorry.
I'll read it. Does the one about the last question we did with the for loop? Does the for loop here print out the error part as well? Shouldn't it stop before encountering the stop iteration error?
Oh yeah, sorry. So it doesn't necessarily like print the error, but it just Python errors internally, so it just stops everything and it just like returns an error, like it gives you the error, but it's not necessarily that the error is being like the error is not from like printing next of I. It's just like when you call that, Python throws that error and then it is displayed for you.
Oh, does it have something to do with the... Oh, wait, sorry. Another question. In lecture, we learned that modifying dictionary while iterating through it will cause a runtime error. It seems like we can edit a list without the error happening, so does this apply only with dictionaries? Actually, I think it's generally frowned upon to loop through a list while modifying it. At least in my interviews, people have frowned upon when I try to do that. So yeah, I don't think it's necessarily specific to list. If you're like looping through a list and popping items or removing items, that could lead to some pretty bad issues. Cool. I think we're just gonna move on for now. Connie, do you know how to get the chat pulled up again? I don't know what the...
Sorry. I think like technical difficulties. I think I disappeared it to somewhere, so let me try to find it, but I'm not exactly sure. If I stop sharing, I might be able to find it again.
Oh
but
yeah, sure thing. I can just take the... No worries, no worries. We'll be switching back and forth. Zoom is hard. What slide am I on? Cool. I'll just keep sharing. Oh, you can feel free to stop sharing if that helps.
Wait, I don't think I have that button either. I'm so sorry.
No, I can maybe share over it.
Yeah.
Yeah,
Good.
let me
Thank
just
you.
do that. Oh my gosh, which one is it? Okay, I think it's this one. Okay, cool. Can people see my screen? Full screen. Okay, awesome. Cool. So now I think this was the last slide. Yeah. Now let's go ahead and talk about generators finally. So honestly, I think the majority of iterators/generators exam questions you'll come across are going to be generators. So this is the fun stuff. As you maybe remember a few slides ago, generators are a specific type of iterator, so they're also iterables, and we create these with these generator functions, where a generator function is any function with the word yield in it. Doesn't matter if it has both return and yield. If it has yield somewhere there, it's a generator function. And when you call a generator function, you're going to produce a generator object. So main takeaway, when you call a generator function, it's not actually going to execute any code. You're just going to create this object. And you actually go through the function by calling next on this generator object to get whatever elements there are. So again, I think of it as an iterator over some sort of function block. So you're going to yield stuff that you write after yield. So generator functions are created with traditional syntax. With the def statement, it's just they have one or more yield statements. And when it's called, it's just going to give us the object. And so this is the key part. The body of the function is not evaluated until you call next or list or something else that calls next. So let's look at a few examples. Here's a pretty simple generator function. So when, again, you create this by having something like def generator of x, 1 divided by 0, yield x. So when we type this code in, quick, what would Python display? X equals generator of 5. Feel free to type in the chat. What do you think is going to happen? Cool. Wow, no one fell for the trap. Exactly, nothing's going to happen. Even though this generator function, right off the bat, just throwing an error at you. It's saying 1 divided by 0. Because the body of the function is not evaluated until we call next, nothing's going to happen. It's just going to say, cool, x is a generator object. So here, it's not going to error. And that's simply because it hasn't executed any code quite yet. Okay, now what's going to happen? We're going to call next on x. Feel free to type in the chat what you think is going to happen. Cool. Error, 0, div error. Yeah, division by 0 error. Exactly. Now it's going to finally give us this error because once you call next, it's pretty much telling us, okay, start a pointer at the very first line. It's a little off center, but it's pointing at this line. Keep executing code until you hit a yield. We basically stop right away. We get a 0 division error. So we start evaluating the function and now we get an error. Cool. So to formalize this process, generator objects, every time you call next, are going to run up to and including the yield statement, and then stop until the next is called again. So it basically has like a bookmark in the middle of your function, if that makes sense. And once you hit the yield statement, it presses a pause button on the function. It yields the value, kind of like a return statement, and then it saves where you are so that evaluation can be resumed. And so when you call next again, you're going to start at the line right under wherever this yield was called. And yeah, this is going to follow the normal flow of program execution that you might expect, which is also why we see a lot of things like for loops and while loops through generator functions so we can keep yielding things. Awesome. And so we really like generators because generators allow for lazy evaluation, which means we only calculate the next item upon request. So just some like random cool usages of generators. This isn't tested on or anything, but if you do stuff with a lot of data, big data, machine learning hype, oftentimes you'll see a lot of data litters with generators because if you throw all of your data at your computer all at once, let's say like 100 gigabytes, your computer might freak out and say, whoa, that's too many gigabytes. But generators allow for lazy evaluation, which means you can create a generator over data that gives you like 1 gigabyte of data at a time. So this lazy evaluation is actually really great. For 61A, we also really like lazy evaluation because we can have infinite generators, and those are super fun for recursion. So it's very common to see stuff like while true in generator implementations, even though in a normal function, if you have a while true, you're probably going to run into some infinite loops because in generators we'll only calculate up to the next yield. So here's a quick example. You might have seen this in lecture or something. If you wanted to make an infinite generator that generates all of the natural numbers starting from 0, it would look something like this. We have our current number is 0, and then while true, we'll yield the number, pause evaluation there. At the next call, we'll calculate current plus equals 1, go back, yield current, and so on. And so this generator what would Python this way would look something like this. Gen naturals, we call next gen, we'll get 0, next gen, we'll get 1, next gen again, we'll get 2, and so on. Quick check for everyone. What happens if after these two calls, I type list of gen. What's going to happen? Any thoughts? Feel free to type it in the chat. Or if you're feeling bold, you can also unmute yourself. Cool. Infinite loop, error. Oh, I actually don't really know. There will probably be an error at some point in time because your computer will run out of memory. So I'll take either. The first step is it's going to have an infinite loop. Because remember, calling list on something is going to say keep calling next until you get a stop iteration. But over here, we're just never going to get a stop iteration. So this is actually kind of like a tricky thing I see a lot where people run into a lot of infinite loop scenarios. Basically, if your generator is infinite, do not call list on it. You'll have a bad time. Cool. Awesome. So let's go ahead and move on. Another summary slide on generators. Our two keywords here are yield and yield from. Yield is going to yield a singular element, whatever you put right after the yield keyword, after a space, and it's going to output whatever you put after the yield keyword the next time you call next on the generator function. Yield from, you might have seen around, is very useful, first of all, in recursion with generators or when you're dealing with iterables. Yield from takes any sort of iterable, so a list, an iterator, another generator, and this is exactly what it does. Yield from list is exactly for element in list, yield elem. So these are exactly equivalent. It basically says for every single item in that list, yield it one by one. One maybe tricky thing is you're totally allowed to do yield from infinite generator because again, it's only going to yield one element at a time. It's just going to stay on that yield from statement forever. So yeah, here's some like different usages of generators. You can use while true if it yields infinite elements. You can use for loops if you want to yield some finite number of elements. And you can also use recursion to make generators. So you might have seen this a lot in practice exams where you see some sort of recursive call and just thing to keep in mind is when you recursively call a generator function, you're going to get back a generator object. So this is why very often you'll see something like yield from some recursive call or for element in some recursive call yield something to do with that. You don't usually want to just yield that generator object directly. And here's an example of that. Let's say we have this generator function yield mults of 3 and you want to yield multiples of 3 of some sort of number. So for example, if you pass in I is 0, you want to yield 0, 3, 6, 9, 12, etc. So here is something that would not really work because if we go through this code, if we have mults of 3i, we'll yield 3 times I. Let's say I is 0, we'll yield 0. And then quick check in the chat again. What's the next thing we're going to yield? What is mults of 3 I plus 1 or mults of 3 1? It's going to be a generator object. So this is not what we want, right? Because we want it to yield 0, 3, 6, 9, 12, etc. We don't want to yield this generator object. So we're unhappy with this. Instead, what we want to do is this code over here. We just throw in a from. We'll yield 3 times I, something like 0, and then we'll yield from mults of 3i plus 1. And the way I think about it is I say, okay, what is mults of 3i plus 1 going to yield? That's mults of 3 of 1. Well, that's going to give us 3, 6, 9, 12, etc. And that's exactly what we want to yield right after the 0. After the 0, we exactly want to yield 3, then 6, then 9, then 12, etc. So you can still kind of use this idea of the recursive leap of faith. It's just instead of like in recursion where you just return the recursive call, here oftentimes you need this yield from or to for loop over it. Cool. I'll pause really briefly for any questions so far. Also, I think I might have missed some private messages. If you could message Connie for now while I'm presenting and me while Connie's presenting, that would be great since sometimes I can't read very fast. Will this also cause an infinite loop? So this is not going to cause an infinite loop because this is lazy evaluation. So when you're yielding from, again, it's the same as for element in mults of 3 I plus 1 yield element. So the next time you call next on this mults of 3 generator object that's created by calling mults of 3, we're going to go to this yield statement. We're going to yield the next multiple of 3, like 3. Then we're going to go back. We're going to continue looping. So we're only yielding one element every time you call next. So this doesn't cause an infinite loop just by calling next. Cool. Oh,
We have one more question. If in the first example we took out yield in the third line, would it produce the same result as the second example? So it would call mults of 3 correctly, but it wouldn't yield it, or like it would never be returned or like displayed if you were printing mults of 3 or like making a list. Well, I guess you can't not make a list of mults of 3, but
exactly. Yeah, exactly. So if you just took out this yield, remember if you're like doing a function call but not really, if you're making a function call but not really doing anything at it, I think of it as just like screaming it out into the void. So if you just type mults of 3 I plus 1, you're basically saying create this generator object. We're not even looking into the code. Just make this generator object, kind of like yell it out into the void because it's not going anywhere, and then stop the function. So that's why we need this yield from. Cool. Okay, so next we're just gonna jump into some practice problems. We have 50 minutes left, so I think we'll have a good amount of time. So Connie and I will alternate going over these, and we'll just talk about the problem, give you a few minutes to do the problem, and then move on to the next problem. And feel free to like type any questions in the chat, but try not to do any spoilers until we're going over the problem. Cool. So let's start off with an infinite list generator. Here we want to implement an infinite generator, which takes in a list. So this parameter is a list, and it's going to yield every element of the list. But when we hit the end of the list, we want to cycle back to the beginning of the list. Do not modify the original list. With any question, especially generator questions, because they get confusing, it's always good to look at the doc test. So let's see. If we create a generator object, which is from calling infinite generator on the list 1, 2, 3, we want to yield each element in the list, which is 1, then 2, then 3. And then when we're done with everything in the list, we want to cycle back and keep yielding 1. And then just to check if people are understanding what this means, what are we going to yield after 1? Type it in the chat. Cool. Yay. Awesome. Yeah, we'll yield 2 after that, and then 3, and then 1, 2, 3, and so on. And there's a little bit of skeleton code here. There's probably some way to do it with recursion, but let's just do it with the skeleton code for now. And I'll probably give like around 3-ish minutes for everyone to get a chance to work through this. If you're done with the question, if you could just press like the, let's say the thumbs up button on participants, pressing it now. Hopefully people can see where that is. That would be very helpful for me to know when to stop. But for now, plan to stop in around 3-ish minutes. Okay, I'm sorry if that was not a lot of time. Maybe we can give more for later questions, but I'm gonna slowly start going over this question. So yeah, for this question, I like to just try to draw out what my game plan is. So feel free to keep working for a little bit. But we have a list. Let's work with this doc test. We got this 1, 2, 3. And if we think about what we want to yield exactly, well, the first thing we want to yield is 1, which is list indexed at 0, then list indexed at 1, list indexed at 2, and then back to list indexed at 0. So the reason I'm writing it out like this is because they maybe give us kind of a hint with this I equals 0 that maybe we can use like a counter pretty much to say, okay, I know at least at the 0th time step I'm yielding list I. Then at the first time step I'm also yielding list of 1. So if we kind of use this I as like maybe a counter to say what time step are we at which yield number are we at, maybe that can be kind of useful. But then we have to think of the problem where we want to actually cycle back. So I kind of have this mapping question where I say I have this counter, but I don't want this counter to exceed the length of my list. So that was a little bit vague. Does anyone want to share their general strategy, either in the chat or you can unmute yourself? Mod, okay. Cool, cool. I see a lot of mod. I see a yield from. That might be possible. I haven't actually tried that version, but anything that works, works. But yeah, I was thinking for this strategy, we could use the modulo operator. Since essentially what we're saying is, well, first of all, let's start with our counter thing. We're going to start with I equals 0. I'm going to basically say we're going to yield something, probably something to do with list. And then every time I'm done yielding something, the next time I'll go I plus equals 1. So now we have I equals 0, 1, 2, 3, 4, 5. But what I actually want is to yield element 0, 1, 2, 0, 1, 2. And you might see this is very useful with the modulo, since for example, 3 modulo 3, or the length of the list, is equal to 0. 4 modulo 3, or the length of the list is 1, 5 modulo 3, or the length of the list is 2. So what might be useful is yielding these elements in this list, which is exactly I, modulo the length of the list. And I think there's probably a few other ways of doing this as well. And who can tell me what is a good while condition here? Cool. Yeah, basically while true, because we never actually want to stop. We just want an infinite loop. So I think this should work. I'm actually not really sure because I'm just noticing this is, if you want to look at the next slide, if you're following along, this is different from the solution on the slide, but I think it should be basically the same. If you want to see the solution on the slide, on the left, using the skeleton code, you could also change this I to just be forced to be 0, 1, 2, 0, 1, 2, 0, 1, 2, and have this I number cycle around. Or you can do this counter thing over here. And yeah, let's show this a little more clearly. So this is one way. The next way is, as you see here, here they just say have I be 0, then 1, then 2, and then after I is 2, then I will turn into 2 plus 1 modulo length of list, which is 3, which will just mean I is cycling back and forth, and in that case, you can just yield list of I. Here's an alternate solution, which is not using the skeleton code, so probably none of you wrote this, where you have something like copy is a copy of the list, and pretty much what you're doing at any time step is, well, copy is starting off as a copy of the list, and then you yield the first element. So you go ahead and yield 1, and then you change copy to be copy sliced from 1 to the end plus copy 0, or essentially you're just rotating the list around. So that works too. And it looks like from the chat, there's probably some way to do it with yield from. If anyone wants to like post their solution in the chat, that might be helpful for people. Cool. Any questions on this one? If not, I think Connie, you can take it away and share the next question.
Yes, I will try to share my screen
Just
again.
override my screen.
We will see. But yeah, our next question we have is called unique. And so for this question, it's from, let's see, fall. Oh, sorry. Yes, it is from fall 2011. And we want a generator function called unique, and it takes an iterable in, and it returns an iterator over all the unique elements of its input in the order that they were appear in the iterable. So basically, like, we also want to not use any for loops, and you also can't use def, for, or a class or a lambda. And there isn't skeleton code, but yeah, we basically just want to like take the iterable and then only yield the unique element. So like if there's any repeated, like we see like one occurs twice, we want to only yield one when it occurs in the beginning, and then don't yield it at the end. And so they should preserve the order. So we see that like we have 1, 3, 2, and then the second 2 is not yielded again, and then we have 5, and we don't yield the 3 again since we've already seen 3, and then we have 4. So we can have like about 4 to 5 minutes maybe to work on this, and we can check back in when it's done. And yeah, if you have any questions, like as always, feel free to drop them in the chat. We'll try to answer. I think it's been about 5 minutes, but if y'all would like want like 1 or 2 more minutes maybe to work on it, please drop it in the chat. Otherwise, we can start going over it. But yeah, okay. Not seeing too much in the chat, so I guess we can look at it and start going over it. So we have an iterable, and we want to make sure that we iterate over all the elements and maybe want some way to keep track of what we've seen before so that we can only yield the unique ones. So maybe if you can drop it in the chat, what are some ways that people thought we could keep track of what we've seen before? Yeah, a list. I see a couple of lists. I think that's, yeah, and using not in, that's exactly right. Yeah, so we can, yeah, we can also use append. So if we create a list maybe, so we see like, oh, we've seen these elements. So first we've seen, oh, sorry. First we have seen nothing, like people mentioned, it was an empty list. And then we do need to iterate over the iterable. So we can we can create an iterator over this iterable. So we say, I equals iter of iterable. And then we should probably have some kind of while loop to go over each element, right? And then after that, I think people were mentioning we can check if the next element was, we've already seen it before. So like with not in or in, and then we can append it maybe if it wasn't in there yet. So we can say it now that we have seen this. So we can have that, for example, the element that we're looking at right now is next of I. And so this is the current element that we're dealing with. And if element not in seen, then as people mentioned in the chat, we can append this element to seen so that next time we check seen, for example, like if we've already appended 3 to seen, and then when we check 3 again, and 3 is that element that we're considering, we see that it's already been seen, so we don't yield it again. And then only in this loop, we would yield this element, since we know that in this loop, it would be the first time that we saw this element. And if we didn't enter the loop, we shouldn't yield it again because we've already seen this element. So that means we've already yielded it. So does anyone have maybe any ideas on how should we fill in the while loop so we can iterate over everything? Yeah, so we can, let's see, yeah, we would say, can we interchange the seen and yield lines? Yeah, you can interchange them because it just stops at the yield statement. So the next time you would return to the line like right below the yield statement if you put the seen under it, and it would still have all the correct variables. So yeah, we can interchange those two. And then we have iterable. Can we use a for loop instead of a while loop? Yeah, we could use a for loop and iterate over all the iterables, or all of the iterables. So we could say like, yeah, like for let's like for I in iterable, and then we could do that instead. And if we did use a while loop, like people were saying in the chat, we could do while true. I think to do this problem with a while loop and recursion, or recursion and yield from, I think you could, but you might need to make a helper function because we might want to keep track of like what we've seen before. So if you wanted to pass this seen list into a helper function and like do yield from that helper function and keep passing seen in so that you can recheck like what you've seen and remodify that list as you go, I think that that could work with recursion. While iterable, I think we could do while iterable if I think if we were like modifying the iterable, like if we were taking elements off of it. But in this case, if we just do iterable, it doesn't like take elements off of the iterable. I guess, oh yeah, that's true. We could do while iterable because iterable is a true statement anyway. So that would work, but you would still need the I equals iter of iterable in order to do that. And let's see, I forgot you could use in for lists and use a dictionary. Would that work? Use in for lists. So yeah, I think using a dictionary would also work. Yeah, as long as we, you could make a dictionary and add these elements that you've seen as keys to the dictionary, and then maybe like a count or anything that would let you check if it was in the dictionary or not. And then why do we yield element and not seen? So seen is most likely like a list of what we've seen so far. So if we look at this example here with 1, 3, 2, 2, the first time we have an iteration, scene would just be equal to an empty list. And then when we yield 1, like, so let's say we yield 1, scene would now have 1. And then we would yield 3, and now scene is 1 and 3. And then it is 1, 3, 2. So I guess if you wanted to, you could like create scene first and then yield everything in scene, but it might not work if iterable is infinite. If you wanted to wait until we've seen everything and then yield it like from scene at once. But like iterable might go on forever, so we might not be able to finish creating this scene list in time. And then how do we not run into a stop iteration error without a for loop? So although it looks like we have an infinite loop because it says while true, remember that for generators, we have like every time we have a yield statement, the like calling, or every time we have a yield statement, like we stop after we yield it, and then we don't like go to the next line or like the next step in the loop, for example, until we call next again. So in the doc test, we have list of unique, which would basically like list out everything in this finite list. So we can do that because we know that the iterable is finite. Like we can see it is only let's see 8 elements. But if like the iterable was infinite, for example, if it was like the naturals iterator, we would not be able to call list on it, but we could have a for loop when we print it out. So only print out certain elements of it. But even though while true looks like it's an infinite loop, it's not going to infinite loop by itself unless you call something that like asks for all of the elements at once.
I think there's a lot of questions in the chat, which is great, since I think this means that this is kind of a challenging question. But maybe we should just move on to the next question for now and continue answering questions while we give you time to work on the next one. If any like students watching this have good answers, also feel free to answer the other students' chats. That would be very helpful. Yeah. I'll just share over this.
And I'll answer some of the questions.
Okay, cool. Oh, where is it? Okay, hopefully y'all can see this. I never know if Zoom share is working. Can someone give me a confirmation that it's working? Okay, awesome. Thank you. Cool. So next one, we have a short-ish question. So generators and higher order functions. We want to write this generator function apply many that takes in one argument function f, so you can call f of x, and at the nth yield, it's going to yield a function that applies fn times. So basically, the first time you call, or the first time you try to get next on this generator object, it'll just yield f. The next time, it'll yield something that calls f of x, f of x, etc. So as always, it's useful to look at a doc test. So what we're saying is, let's say we're passing in a function f, which is just going to double whatever input we have. We create our generator object, gen equals apply many of f, and then this is basically the same, basically shorthand because I ran out of space, of saying call next on gen called on 1 several times. So another way of representing this doc test is say next of gen is going to give us a function, and this function called on 1 is going to give us 2, or in other words, f of 1. So this is the same as f of 1. And then calling it again, next of gen of 1 is, oh my god, is going to give us 4. And this is the same as f of 1. And then finally, calling it again next on gen of 1 is going to give us 8. Or in other words, f of 1. And maybe a check. What is next of gen of 1 after this going to give us? I'm going to type it in the chat. 16. Awesome. Exactly. That's going to be f of I don't know how many f's I said. 4 f's of 1. So it's just going to keep calling this function on it. If there's any questions on this question wording, please message, because I wrote this like an hour ago and I'm not sure if it makes sense. But here's our skeleton code, def apply many f. You don't have a lot of lines to work with, but you know, you got a for loop, you got 2 empty lines. And yeah, let's work on this question for, let's say, 4 to 5 minutes. Again, feel free to post any questions in the chat. I'm going to unthumbs up everyone. So please hit thumbs up when you're done with the question. And if people are stuck, you can hit like a no if you're stuck and I can give a hint. I have no idea how long this question is supposed to take, so can people generally type in the chat how many more minutes you think you might need? Like 2, 3, or give hint? Cool. Okay, let's give a hint. So let's kind of build up to this hint. There's not a lot of lines of code to work with, right? Like when I wrote this question, I was thinking we should do some sort of iteration and I don't know, like loop through some numbers and have a counter, and that would be really cool. But unfortunately, we just don't have a lot to deal with. We need yield somewhere. We are probably going to have to yield somewhere here, right? Because we need to yield many things. In fact, we need to yield basically infinitely many things. And since we probably need a loop, but we don't have anything to loop through, like you can't do like for I in range 100 because this is an infinite generator. This might actually be a hint. Maybe we should use recursion. In fact, since this is a hint, we should definitely use recursion. I'm going to default to like another minute or so. I'll give one more hint. Okay, for the sake of time, I'm going to start going over this. Again, I apologize. I think for most of these questions, we're probably not going to give you as much time as you would even have in an exam, just because we want to get through the questions. But yeah, so for this question, my hint was you probably want to use some sort of recursion. So that means that we're going to call apply many on something. And again, the way that I reach this is usually you can figure out what strategy you want to use through trial and error. So for me, if you try to do this with iteration, but you have this for loop over here, you might think, okay, I can't do while true. How the heck do I do a for loop over an infinite number of stuff? I can't do for I in range something. This maybe means that we shouldn't just do iteration. Maybe we should do some sort of recursion since this is an infinite generator. So then the question is, I'm going to call apply many on something. What should I call apply many on? It's going to be some sort of function f. And at this point, you might think I have two options. I can either just call it on f again, or I'm going to create some sort of new function. I'm going to create maybe some lambda function that applies f twice or something like that. Maybe you can do it this way. I actually haven't tried it doing this way, passing in a new lambda function that you call it on, but you'll actually soon figure out that it's actually very complicated to create a function that calls itself twice. There's some like scoping things that causes a bunch of infinite loops. So for this function, I'm going to say we're not going to change f. We're going to loop over. We're going to make the recursive call and loop over for func in apply many of f. And this looks super weird pretty much because it looks like you have an infinite loop, right? You're like recursing over itself. But that's the magic of generators. Because of lazy evaluation, this isn't going to cause an infinite loop. So let's actually take a step back again and look at our doc test. When we call apply many on some sort of f, for example, this f that just multiplies itself, the very first time that we call it next on it, we're just going to get f back by itself. So before we even start looping and doing any crazy recursive magic, the very first thing we can do is probably yield f right off of the bat. So we want to yield f, and then we'll go into this for loop, and let's try to visualize what this for loop looks like. So apply many of f is going to give us this generator essentially. I'll try to draw this out, where the first thing we generate is going to be f. The second thing we generate is going to be f of something, this function f of. The third one we generate is going to be f of something, dot, 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 etc. And the way we want to transform this is, well, off the bat in the first time step, we yielded f. Next, we don't want to yield f again, right? We don't just want to say for func and apply many f, yield func, because then we're going to yield f twice in a row. Instead, we want to take every single function here for func and apply many of f, and apply f to it one more time. So we'll, instead of yielding f right off the bat, we'll yield f of f then will yield f of f of f of, etc., then f of f of f of f of, etc. So in pseudocode, for func and apply many f, yield f of the function of whatever parameter. And the way that we do that in practice, throw back to higher order functions, is we can use a lambda function. So we can yield a new function, lambda, that still takes in one argument, just like f. We said f is a one argument function. And this is going to yield f of whatever you just generated from this recursive call. So here it's f of f of f of f of f of f of, or in other words, you're going to yield lambda x, f of func of x. So this is just saying for every func that you generated, apply f to that and then yield that function. Okay, so I feel like this is like a deceivingly short function, which is kind of complicated. So yeah, any questions?
We had some from the chat. Why would modifying the parameter in do yield from apply lambda x f of x as the second line not work?
Wait, sorry, could you repeat that one more time?
Yeah, sorry. Why would modifying the parameter in do yield from apply many lambda x f of x as the second line not work?
Apply many of f of x.
Oh yeah,
Okay.
it was a lambda x.
Oh,
yeah, f of x.
lambda x f of x. You know, that might work. Feel free to test it out and see if it works.
I think people are also having trouble with Python tutor. I did try to type it in and I think it was fine, but people said that they got free variable func referenced before assignment.
That's a really good point. I also got that. There was actually a Piazza post about it. I don't know what's going on, but code.cs61a.org is having some errors with just generators and higher order functions specifically. So I think if you click the little bug button to see the environment diagram, it ends up working, or just try it in your local Python shell. It's a bug with code.cs61a.org.
And people were asking if we could re-go over the for loop, maybe?
Yeah, sure. So the for loop is saying, for apply many of f, if we use the recursive leap of faith, we know that apply many is going to yield f, and then it's going to yield f of something, and then it's going to yield f of f of something. Wait, I don't know if I said the numbers right, but it's going to yield like f called once, f called twice, and then f called 3 times, so on, using our recursive leap of faith. And then what we want to do is, well, we don't want to yield f called once, twice, 3 times. We want to yield f called twice, 3 times, 4 times. So this line down here is just saying call f on it again. And I agree that probably this yield from thing, if it works, is better. But this is the skeleton we gave you, so too bad.
And then we also have doesn't apply many actually just have one function to loop over, so just f, yeah. And do we need a for loop necessarily?
I think you can probably do this yield from thing. If anyone can just confirm that this works, I feel like it does. But if anyone has like Python pulled up. I'll do like one more question. Could you explain how the for func and apply many f changes f to be f of f? Yeah, so the for loop doesn't really change f to f of f. The for loop basically like emits the f and then the f of f, etc. This line down here, specifically this part, is going to change f into f of x, and it's going to change f of f into f of f of x. Could you repeat what the yield from part says? Yeah, let me go on to the next slide so y'all don't have to read my handwriting and can read actual text. So this is like the cleaning of stuff. Oh, the yield from doesn't work. Oh no. Okay, that's good to know. Yeah, brownie points to anyone who figures out a yield from that can work. Okay, I think let's just move on to the next question. I'll try to answer all the rest of the questions on chat. Cool.
Yes, I will share my screen. Yeah, we wanted to include one of the like interesting function questions where it's like higher order function and generators, but I know those are really confusing, but I think there's another discussion question that was like repeated. That's a good practice, but it's like good to like try to think about like what's happening at each step, but it's hard to think about sometimes because you're like f of like, and then there's a bunch, but hopefully practicing helps a little bit. Our next question is about trees and generators. So we have fall 2017 question. And so we have a level order traversal of a tree traverses the root of T, level 0, and then the roots of all of the branches from left to right. Oops, let me annotate. So the branches from left to right. So in the example displayed here in this tree, we want to have 1 visited first and then 2, 3, 4, since 2, 3, 4 are 1 level below 1, and we want them from left to right. And then after that, 5, 6, 7, 8, 9. And we want to create a generator function to yield the labels of a tree in this specific level order. And we want to use a helper function that yields nodes at 1 level and then call the function by increasing the level at each call and until we find that there are no more levels and there are no more nodes in the tree to yield. And one of the things it says here is that you might not need to use all of the lines. Let's see, yeah, so we just have a function definition, and then we have the helper function that they were talking about, def 1 level. And so the idea is to use the helper function to only concentrate on 1 level. So if I tell the helper function only yield things from level 0, it will only look at that. Or if I say only yield from level 5, it only needs to worry about level 5. It doesn't need to worry about let me yield level 0 and then level 1 and then level 2. And then what we can do is we can worry about that here in the rest of the function. And we have these variables in the skeleton code that are assigned to us that we can maybe use. So we can have maybe 6 or 7 minutes and we can check in after that. It's a little bit of a long question, but we are running a little bit short on time. But once you're done, if you could put thumbs up in participants or drop in the chat, that'd be super helpful. Thank you. Oh, sorry, this is using the tree object. So not the functions, just the tree object that has the attributes, and you can do dot label and stuff. Okay, I know this question was a little bit long, but in the interest of time, we can start going over it, and then we can answer questions as we go. Hopefully, you got a good idea of like maybe some ideas of how you would approach it. Um, but I guess we could look at first in the skeleton code, we have this line that was provided to us, level equals 0 and count equals true. And we see while count. And then inside of the while loop, we change count to be 0. And we do know that 0 is a false value. Um, so perhaps like if we don't go into this for loop and we don't change count on this line or the last line, count will be 0 and then the while loop will stop. So maybe that's something we can keep in mind and can help us stop when we don't have any more labels. And so we know that we would want to maybe use one level. So if we take a look at one level, we see that it takes in K, which is the like level that we want, and then the tree itself. Oh no, one second, sorry. Oh wait, one second. Let me. Okay, sorry about that. Okay, so we takes in K and it takes in the tree itself. And so when would we maybe want to yield K itself? Or sorry, not yield K itself, but when would we want to maybe yield the tree's label itself? Yeah, sorry, I don't necessarily enjoy playing those games, but I got them for my club. But yeah, after the for loop, let's see. So if it's a leaf is a great idea. Yeah. So if it's a leaf, K would be 0, right? So we know that if K is equal to 0, then we're at the level that we want to yield and we don't have to search downwards anymore. So we can just yield tree.label. Otherwise, we can go into this else statement and see that for a child in blank, maybe do some recursion, maybe if anyone had any ideas. So yeah, we have tree.branches. So if this isn't the correct level, we want to explore further down. And to do that, we would need to look at the tree.branches. And maybe what could we yield or yield from? So yeah, it is a recursive call. Yeah, that's a great idea. So we have one level of child and then k minus 1, since we know we went down a level, so whatever level we were exploring for, we've now explored one level, so we can go subtract one level and then see if the next one is the correct level to yield. And we do need to yield from, like people mentioned in the chat, because one level is a generator itself. So if we want to yield everything in a function call, we need to yield from it. Now we can take another look at this while loop. So we have while count equals 0, and we're probably going to have to call one level here. And like the problem description said, we want to yield everything from one level and then like maybe increase the level and then yield everything from the next level so that it's from left to right and it goes from the topmost level or the lowest number level to the highest number level. So we have that count equals 0. And maybe do we need the line under the count equals 0, or like is there anything else we need to do before we go into the for loop? Yeah, otherwise we can look at the for loop. We can ignore this line for now since it did say you might not need all of the lines. So if we don't find anything to put it there. Yeah, so we can assign it to the recursive call if we would like, or we could put the recursive call directly into the for loop. So the for loop could be one level of tree, and then we have, the tree, and then we have our level variable that we're setting. If we did put pass, it would like skip the rest of the function, but we could just like not write it with the like line, but we cannot write the word pass or else it will not continue the rest of the function. And then in our for loop, what would we like to do maybe for each of the labels in one level of tree? Yeah, and so we can yield the label, exactly. And then since we know that this will tell us everything from like starting from the 0th level, since level starts at 0, and then we keep going. Oh, pass only skips one line. I'm not sure about that. I can see that. So yeah, they said change count equals true. Yeah, that could work. Let's see. We could say count equals true. We could also say count plus equals 1, or just any truthy value to know that if we went into the for loop, we know that this level had some labels to yield so that we know that we can continue our while loop. But if it didn't go into this, we know that we don't have anything else to yield. So we can just leave count equals 0, and that would be a false value. So the next time we go into our while loop, we'll have while like a false value, and we wouldn't continue. Sorry, so someone said we have pass and it works fine. So that should be fine then. Sorry, my bad. I guess ignore things that I said about pass. And then at the end of the for loop, we just need to increment our level, right? So then the next time we can explore the next level downward and continue yielding from the tree until we have no more count. So yeah, we did not use the line after the count. And I know people said that skeleton code with extra lines is very annoying. I'm sorry about that. I think we don't tend to see it unless you go back to maybe like fall 2015, 2016, 2017. Usually Professor Hillfinger tends to like questions that have skeleton code with extra lines. I don't think I've seen it too often, like recently, but it's still possible. But just keep in mind that like most lines have a purpose, but I guess if you don't like have anything else to take care of, you don't need that line. But like someone said, you could have just put like like call like I don't know like the level equal, or like I guess not level because we already have a variable like that. But something sorry, tree dot label. So here we have like for label in one level, so that's just the thing that we're yielding only. But tree dot label would be yielded if we were like once we go into one level of tree and then 0, we would get back tree dot label and we would be able to yield that. But some people were saying earlier that we could have put the recursive call on the line above and just to use that line. So you can use the line, but it's not necessary. And then let's see, can you explain why we need to yield from one level child of k minus 1 instead of just calling one level? Yeah, so if we just call one level again, we're just going to set up the generator function and like create it. And but if we don't yield from it or like call it at all, it's just an object that's sitting there. So we're not going to be using anything that it yields or returns because we're not translating that and putting it back into a function where we actually like output that value. And then at what point in this code do we yield labels from level 1, etc.? Because doesn't one level only yield the root label? So one level yields the root label if the level is equal to 0. But for example, if we say like level is equal to 1, so in the second iteration of our while loop, when level is equal to 1, when we call one level of tree and level with 1 as level, we would see that k is not equal to 0. So we do not yield tree dot label and we do not yield only the root label, and we would go into the for loop and we would say for child in tree dot branches, yield from one level child k minus 1. So then this would be converted to child and then 0 if k was originally 1. And so when we visit each of the branches, and so that'd be like in our example like 2 3 4 or yeah 2 3 4, we would see that k equals 0, so we would yield tree dot label, and that would be the label of everything in level 1, for example.
I think we're running up against time. So really quickly, if you gotta hop off, thanks for coming. Thanks so much for coming. If you still have some more time, I know we have one more question that we didn't get to. So if you're interested in hearing that question, maybe hit a thumbs up and I can stick around and go through that one. Cardi, if you gotta go, that's totally fine. I just wanted to make a very quick announcement, very important announcement. So the official 61A meme thread that has been a semesterly tradition for at least one semester is now out, and I've been procrastinating on studying, so if anyone wants to post any memes, that would be very much appreciated. I'm sad that there's none right now. But yeah, it looks like there's 12 thumbs up, so I'm going to stick around and go through the last question on the slides. This will all be recorded, so if you can't stick around, that's totally fine. Thanks for coming thus far. And yeah, I'll just continue on. Oops. Is this sharing? Okay, cool. So yeah, our last question is this power generator one. If anyone was here for a Make Generators generator for midterm 2 review, maybe you're getting some painful flashbacks because I know I am a little bit. But power generator is a function. I swear it's better than Make Generator generators. Oh, I don't know why it says implement the generator function pow_naturals. Well, pow_naturals is the function name. It's going to yield generator objects, and each generator object that it yields is going to infinitely yield the sequential powers of a natural number. So we've got this doc test over here, where generator is pow_naturals, and here we have 3 generators that it's yielding. The first one, P1, is going to yield, let me just write it out. Oh no, don't look. P1 is going to yield the powers of 1. So this is going to yield 1, 1, 1 forever. P2 is going to yield the powers of 2, or in other words, 2, 4, 8, 16, etc. And P3 is going to yield the powers of 3, in other words, 3, 9, I cannot do math, 27, I don't know the next one, etc. So that's basically what this stock test is saying right over here. Cool. So now we want to implement POW naturals. Let's see. So I'll just give you a general structure. So oh my gosh, they give you this helper function over here, POW NP, and this is a generator function in itself. And then to actually start yielding stuff, that's this code down here where you're going to yield. This should hopefully be generator objects. And I don't have a poll set up for this, but I know it's getting late and people might have like Zoom fatigue. So just type in the chat if you would like some time to do this problem, or you would just like to hear me slowly go over it. Okay, time. Awesome. If anyone types in how many minutes, I'll just go with that. Both. Well, I will definitely go over it then. Okay, lots of different ones. My quick math says you'll get 4 minutes, 3.5 minutes. Okay, yeah, we'll give you 3.5 to 4 minutes to do this one. Then I'll go over it. Oh, yes, there is another line below the last yield. I'm sorry, this was not very well laid out. I have no idea how long it's been, to be honest. So if y'all could post in the chat if you have a second how much more time you would like, that would be great. Okay, okay, people are good. All right, cool, awesome. Okay, I'm gonna go ahead and say that was 3.5 minutes then. Cool. So again, oh, let me resume sharing. If you didn't see, there is a line down here. I'm sorry, I also forgot that there was a line down there. But yeah, let's go through this. So the way that I would probably run through this code is say, okay, the first off, the immediately important part is that we need to generate generators. So the part of the code that actually aligns with the outer function where we're going to generate stuff is out here. So what do we have to work with? We've got this counter variable n. We have probably some sort of loop over here. We got a yield statement, and then we got another line. So off the bat, I'm probably thinking maybe we can have some sort of counter. And what do we need to yield? I erased this, but we need to yield generator objects. And unlike function objects, maybe there's a lambda equivalent of generators, but we've never seen that. So in order to yield generator objects, we need some sort of generator function. And wow, how convenient. We have a generator function right here. So that's maybe a hint to me right off the bat that we might be yielding some sort of calls to POW over here to yield generator objects. But they don't really tell us what exactly POW does, so let's figure that out. POW is a function that takes an n and p. It's going to yield stuff since it's a generator object, and what it yields is basically up to us. So let's think, what is a useful generator to yield? Well, at the very first time step, I want to yield a generator object that yields 1, 1 to the power of 2, 1 to the power of 3, etc. Then for the second one, I want to yield 2, 2 to the power of 2, 2 to the power of 3, etc. So you might be able to see that there's like basically two different numbers that are at play here. We have the number or the base that we want to yield, and then we also have the power that we want to yield. So this might be kind of a hint for the two numbers here. And I don't think it matters which one's which, but I'm going to go ahead and say n is going to represent the base, like 1, 2, and then 3 next, and p is the current power that we're working at. So for example, in the very first call, we'll want to yield something like pow of 1, comma, and what power do we want to start at? I believe we just want to start at the power of 1. So what is that? Well, here, to put this in words, since that's always important, pow is going to be a generator function that yields all the powers of n starting from p. So pow of 1, 1 is going to yield all of the powers of 1 starting from 1. So off the bat, the first thing that we want to yield is clearly going to be n to the power of p, or 1 to the power of 1, or 2 to the power of 1, or 3 to the power of 1. And I don't think we've seen a lot of exponent raising these days, but that's going to be n just to the power of p. And then we have this yield from call. We know that this is going to be an infinite generator because it's going to infinitely yield the sequential powers. So that gives me a hint that maybe this is going to be a recursive call. So what do people think this n, I just keep it away. This first parameter should be n. Since we're not changing the base, what do people think the second parameter should be for a recursive call? Oh, cool. I see Carlos and Jonas already said p plus 1 or 1 plus p, both should be good. Exactly, because we're going to yield n to the power of p. And then what else do we want? We want n to the power of p plus 1, n to the power of p plus 2, infinitely. And the generator that yields all of this is going to be exactly pow of n comma p plus 1. Awesome, so we're done with this pow thing. That's pretty useful. And let's go back to why we created this. We wanted to yield generator objects, and we want to yield, to write it out, we want to yield pow of 1 comma 1, then we want to yield pow of 2 comma 1, pow of 3 comma 1, etc. So I know that I'm always going to start off my pow with the power of p being 1, but what's going to be changing is this n parameter or the base. I want the base to go up by 1 every single time I yield a new generator. So conveniently for us, we start off with an n equals 1 out here. So at the very first time step, we'll yield pow of 1, 1. But you might have also gotten this just because n kind of looks like a counter here. Every time we continue looping, we want n to increase by 1, or n plus equals 1. And final step, we need to fill in this loop. Any ideas for what sort of loop we might want here? Cool. Preeti says, well, true. Exactly. There's a lot of infinite stuff going on. So Pow Naturals is an infinite generator that yields infinite generators. That's pretty exciting. So we're going to yield infinite numbers of these generators. So here we're just going to have while true. While not false also works. In fact, a lot of things could work here. You can do your most creative thing. Cool. Any questions on this? Could we have used a for loop like the last question? Maybe. I don't really know where we could use a for loop. Since for loops tend to be with finite things a little bit more. I'm sure there's some way to use the for loop in like a creative manner, but I'm just not really sure how to do that right now. How does the two yields in a row work? Um, I'm not sure which ones you're talking about. Maybe these two. So this is basically saying the very first call to next, you're going to yield n to the power of p. And then for the rest, you're going to, this is the same again as for, let's say, x in pow n comma p plus 1 yield x. So you're going to yield n to the power of p, and then you're going to yield everything from pow of n comma p plus 1. Cool. And yeah, since it's 5:15 and we're super over time, again, for anyone who needs to go, feel free to hop off. Thanks again for coming and sticking around. The recording should be posted soon. And yeah, Con, if you gotta go, feel free to go. Thanks for sticking around for so long. I'll just stay around for if anyone has any last minute questions about anything. But yeah, thanks so much.
I have a quick question.
Yeah,
For
sure thing.
the unique function that generate why like finally we yield element instead of like the same list that we created.
For the unique, oh, okay, yes. Let's go back to that one. Oh no, I skipped it.
Oh,
Okay.
yeah. So yeah, the list is like it holds everything that we've seen so far. So I guess we could collect like everything from the iterable, and then like that would only be like it would technically be a unique list, but if the iterable was infinite, we wouldn't be able to finish generating the scene list before we yielded anything. So instead we just look at one element at a time, and if it's not already in the list, we can like yield it, and then we can say like, oh, I've seen it and put it into that list.
Oh, thank you.